Hey, welcome back to Fat Mama Physics. In this video, we are going to finish off our last question on the photoelectric effect. This is going to be question 1C, in which it follows the graph here of the maximum kinetic energy ejected by an electron as a function of the frequency of light used for this metal. So we started off this question in this previous video here, and question C is going to relate all of this to what we call the stopping voltage, okay? So let's take a look at what these calculations could look like. In the following diagram, so this is grabbed directly from this is your PhET simulation. The negative terminal of the power source is connected to the plate where the electrons are collected. So what that means is, imagine light, photons come out of this lamp and whatnot. These electrons on this metal plate gets ejected, and then they, with some amount of kinetic energy, are going to approach this other plate, in which it will generate a current, an electron current, not the conventional current, in that direction. The electrons are going to move this way. However, if we apply the negative terminal in that direction, meaning if we take this battery and we swap it around so that the negative terminal is on this side, meaning that the electrons are going to feel a repulsion off of this other plate. This repulsion means this electron is not going to like to move to the other side of this plate, meaning that in order for this electron to make it over to the other side of the plate, it must have enough kinetic energy to overcome this electric potential. And this electric potential is provided by this battery, so whatever this battery is going to read. If the battery applies enough voltage, enough electric potential between these two plates, then these electrons may not move over to get to the other side of the plate, meaning as a result, no current will be detected in this wire with no electron making it across. So that's kind of the idea of what's happening here. So light of this wavelength is used to shine on the metal surface. The voltage supplied was increased so that no current is detected, meaning that this battery supplies just enough potential difference so that this electron just doesn't make it across. So potentially this electron reached exactly 0 speed right before it hits the plate. So it just doesn't make it across. Meaning, whatever kinetic energy these electrons had at the beginning right when it's ejected, that amount of kinetic energy is going to be all used up, turning it into electric potential energy as it is moving across to the other side of the plate. So, what is this voltage called? This voltage is called, as what I was said earlier, this is called the stopping voltage. This stopping voltage provides the potential difference required for an electron just to not make it to the other side of the plate. So whatever residual kinetic energy times the charge of an electron is going to give us this this potential difference applied across this plate times the electric charge is going to be equivalent to the kinetic energy of these electrons ejected, meaning that, let's say these electrons usually would have the same kinetic energy, but but the maximum kinetic energy, it means for no current to exist, means that the electrons, even with the highest kinetic energy, does not make it across, meaning that this is going to be equivalent to the maximum kinetic energy a electron could have after it is being ejected, okay? So it stops all the electrons. It cuts off even the highest the fastest moving electrons. What is the voltage supplied? What is the voltage supplied? So we just talked about it right here. And what we need to do is we need to figure out what is this EK max. Meaning, we are going to need to use this wavelength of light, to figure out the amount of residual kinetic energy. So it means that this amount of energy, some of it is going to go into the work function of ejecting the electron. Whatever is left over is going to go into the kinetic energy of these electrons. So we have to account, so whatever energy this gives, we have to subtract the work function, and that's going to give us the residual kinetic energy before we go ahead to find the stopping voltage, divided by the charge to find the stopping voltage. But since this is continued from the last question, we should stick true to the graph. So what we're going to do is, this amount of light has a wavelength. It's going to be associated with a frequency, and that's going to give us the kinetic energy of the electrons ejected in electron volts. So in fact, we don't even need to do any sort of calculations with subtracting the work function, which we could. Hopefully you've gotten those questions correctly, so that you won't carry this error moving forward. So it's probably better just to refer to the graph in case you did make a calculation error earlier on. So converting this to frequency, we know that the frequency of light is going to be the speed of light divided by the wavelength, which is 3 times 10 to the power of 8 meters per second, divided by this wavelength, which is 187.5 nanometers, so times 10 to the power of negative 9 meters. And this is going to give us 1.6 times 10 to the power of 15 hertz. Okay, so that is pretty nice. I think that's even on a graph. 1.6. I'm going to use maybe blue in this case. So 1.6 is about right there, and it touches the graph at about here. And unfortunately, it doesn't show very well exactly where this is going to be. So you're going to make a rough estimate of exactly where this line intersects this grid here. So it looks like it's right about there. It's a bit shy of 2.2 electron volts. So probably about 2.17. Or 2.15 probably is fine. Okay, let's just go with 2.15. Usually on an IB marking scheme, it gives a margin of error if for estimation error. So you'll be fine with saying this is about 2.15. Okay. So that giving us electron volts, in order for us to calculate the amount of kinetic energy in joules, we would have to multiply this by the elementary charge E, which is 1.6 times 10 to the power of negative 19 joules per electron volt. But I think we can kind of get away with that, because guess what? EK is equal to the stopping voltage times the charge, which in our case is an electron. So if we use V, and I'll use Q here has an electron, charge an electron, this is going to be equal to 2.15 EV times E itself. And the nice thing is that these are going to cancel out very nicely. So, and of course the units are going to stay behind. This is going to be joules per electron volt. And this over here is going to have a charge of a coulomb, okay? So after we cancel all of these out, the units are going to be in, this EV goes away, so that's going to be joules divided by coulomb, or coulomb to the minus 1. But our answer is going to be 2.15 joules per coulomb, or in other words, 2.15 volts. Okay, so that is our stopping voltage for light used for, the wavelength of light here used. Okay, so now we want to calculate the maximum speed of these ejected electrons. So now we know the stopping voltage. We have the maximum kinetic energy, which is 2.15 electron volts. We want to use this to figure out the speed of these electrons. So since this is equivalent to the kinetic energy, and we know that kinetic energy if as electrons are 1.5 mv squared, we just directly used electron volts, find the energy in joules, divided by the mass, multiplied by 2, etc. So basically doing algebra. And just to mention that I need to multiply this by 1.6 times 10 to the power negative 19, so I'm going to put that E in there as well. Okay, so doing a bit of algebra, this means that I am going to times both sides by 2. I'm going to divide both sides by the mass. And not to forget, I have to divide take the square root of both sides to get the square root of... to get the speed by itself. So ultimately, my speed is going to end up with the square root of 2 times 2.15 eV times 1.6 times 10 to the power of negative 19 EVs per joule, actually joules per EV, divided by the mass of electron, which is, from our data table, 9.11 times 10 to the power of negative 31 kilograms. And that's going to give us 8.69 times 10 to the power of 5 meters per second, or to 2 sig figs, 8.7 times 10 to the power of 5 meters per second for the speed of an electron, maximum speed of this electron. Okay, so there we go. There is our question for stopping voltage. So basically taking the battery, swapping it around so that you essentially apply a potential difference to hopefully stop these electrons from making it over to the other side, meaning they won't generate a current, and your stopping voltage would have stopped the electrons going at the fastest speed, so therefore that is equivalent, or you can find the equivalent maximum kinetic energy of these electrons. Okay, so there we go. This is the question. So hopefully you learned something from this question that you can apply later on. I thank you for watching, and Fan Mama Physics signing out.